thank you, Vitek and IBM, for hosting us. Tonight we have a great show. Jan Vitek from Northeastern is going to tell us all about his work in making R run on, well, I think the LLVM, but perhaps more general than that. So Jan is actually fairly new in Boston, just a year or so. He's from Purdue. His specialty is, I guess, compilers. He's more of a computer scientist than a statistician, but his wife, I think, is a statistician. So, and let's see. So I think you're on the board of SIGPlan or some on the board of SIGPlan. So Kurt has, so just very briefly, next month, or actually coming up in about 2 weeks, we have another one. 2 weeks we have Max Kuhn. He's coming up, he's talking about Quinlan's Cubist package, rule-based decision tree. I've seen it before, it's a good talk, and then we've got to figure out what we're going to do. So if you want to talk about, if you have some ideas about what you want to see next, please hang around after the talk and we can discuss that. If you have some good ideas or you know someone you'd like to see, we can try to arrange that. So with that as an introduction, let's see, so restrooms are out and to the right. I don't guess there's too many other logistics, and so I'll turn over to Jan.
All right. Hello. So it's a pleasure to be here. As was mentioned, I'm a computer scientist, statistician by alliance, by marriage, transitively a statistician. I've been told that I have to do good by R, otherwise ... So that's what I'm trying to do. So for this talk, so this comes from a computer science perspective. Not entirely sure what's the background of the audience, so I will let you, tell me, and please feel free to interrupt. I've prepared some material, but I'm happy to veer off in any direction that makes sense to you. Okay? All right. The other thing I want to say ahead of time is this is work in progress. So R doesn't run that fast yet, but we're working on it. So there's so some of it is also about what are the challenges, where is this going, what are the prospects, but not necessarily that we have great results yet. All right. Okay. Yeah. So feel free to interrupt at any time. So before going further, the first question is, well, is R actually slow? So fair question, one can ask. And so we did some measurements. They're not very extensive, but let me present them to you. So these are results where we took 12 programs from something called the Computer Language Benchmark Game. It's a website that has a variety of simple problems, and what is nice about it is that these problems have been coded up in pretty much every possible imaginable language, and we can easily compare across languages. Is this a scientific study? No, but it does give a data point. So the data that I'm showing here is comparing the 12 of those programs, and what we did is we normalized the running time of those programs to the running time of the C version. So 1 is the running time of C, and then we're comparing the running time of Python and R. So Python is in blue, R is in red. And the scale is a log scale. All right? So that's the setup. So what can we see? Well, we can see that Python, this is I think it's an average, is roughly around 50 times slower than C for this set of programs. Why is Python slower than C by 50 times? Well, Python is an interpreted language, and essentially this is the cost of a fairly slow interpreter running. Completely unsurprising. And then you look at the R numbers, and the R numbers are somewhat higher. So, say 400 times slower than C. on these 12 programs. Okay? Well, that's a data point. We'll come back to, well, maybe I should say, is this representative? Is this meaningful? Well, these 12 programs are very computational tasks. They don't use any statistic libraries. They don't go to any too much C code. So this is, you know, sort of your worst case. This is if you were to code up from scratch everything in R without, you know, going to libraries, you're about 400 times off C. Okay, that's a data point. Yeah.
What happened with S6 and S8?
So these two were ones that actually didn't run in Python. So yeah. Wasn't the object of our study, so we just said no, whatever, leave it alone. So the next question we can ask ourselves is, well, assuming that R isn't as fast as it could be, where does the time go? All right. So for that, what we took was a more representative set. So we took programs from vignettes from Bioconductor. We took about 100 of them, the ones that ran the longest. And then we instrumented the R interpreter to get a breakdown of costs. And then try to sort of understand where the time goes. And this is roughly what it looks like. So each one of these thin stripes is one vignette. The y-axis is percentage of total execution time. And then the colors represent the different cost centers that we identify. Let's see. So these colors are a little bit washed. I'll just show you on these. I think it's a little bit better. Hope everybody can see. So what are the interesting things to pick out? So first, if you just look at it from afar, each program has a kind of different color map, right? So what that means is, it's not like there's one thing that is the cost for R, and if I fix that one thing, R will be wonderfully fast, right? Costs are spread. So you can notice the red is prevalent. So the red are your built-ins. So it's essentially when R goes to a built-in C function and does stuff outside of the interpreter in C land. Well, and what we can see is, you know, there are some tasks, like the last one, which is, you know, completely dominated by built-ins, and, you know, a lot of tasks are not, and it just varies a lot. So it is certainly not the case that R, and then the other point here is the light blue just before the built-in is external, and again, for instance, this task spends a lot of time in external C functions and a little time in built-ins. But it isn't the case that all of the time is spent outside in C code. You know, that would not, you know, saying that, oh, you don't need to worry about the language, it's all the C code cost, that wouldn't be true. So what are the costs we identify? The memory manager, which is the garbage collector, allocation of different elements, duplication of vectors. So for instance, that purple here is duplication of vectors. You can see here, there's one program that spends probably 70% of its execution time duplicating vectors, right? And on average, it's about 10. Lookup, when we are looking for names. Match, it's when we're trying to figure out what order to give the arguments to a function. External built-ins, arithmetic operations, specials. Yeah?
The sort of purplish along the bottom, is that?
So they start, this is the memory manager. So the order is reversed.
Ah, okay.
So we should have
Yes.
swapped those.
Okay.
So
Yeah, that makes sense.
Well, and actually, I'll have the next slide is actually picking all of the memory management costs together. So this is interesting. So this is putting all of the costs of, yeah, I think you can see it here, all of the cost of allocation, garbage collection together. And, you know, if you say this is 30%, you know, yeah, so it's like half of it are under 30%. And then you have some programs that are spending all of their time managing memory, right? Okay. So I think what this shows is that cost in a language as rich as R come from all sorts of things, and your programs will exercise different parts of the language. So, you know, it's really, I think the main takeaway from this is there isn't a single magic bullet we can apply to speed up R. We really have to look at the whole thing and try to push down on every single cost. Now, if you think about it, if you think, well, those programs are 2 orders of magnitude slower than C, then we should be able to push down a lot of these costs by a lot. Maybe. Another interesting picture is the cost. Another interesting picture in terms of performance is memory pressure, right? So even if I am willing to be very patient, if I can't fit my computation in my available memory, yeah, that's not going to work out, right? So we need to make sure that R's memory usage is reasonable. So here's again our 12 small programs, and the data set here compares the dynamically allocated memory in C, so all of your mallocs in blue, and then on a log scale, the allocation of the user data, you know, the payload of your vectors, and all of the internals, you know, all of the language objects, all of the other things that the interpreter, your lists of arguments, all of the other things the interpreter has to maintain, okay? And so what you see is, well, there is clearly several order of magnitudes more memory allocated in R, and that's not surprising if you know that a single integer, a scalar integer, takes 56 bytes, right? That's a lot of bytes for that payload. The number is 0. But the other thing that is important to note is that all the metadata that the interpreter manages behind the scene dwarfs the user data. So whatever useful data you're allocating, the interpreter behind the scenes for you will allocate way more in its own sort of data structures. And if you look at the C program, there are very few C programs where R and C have about the same memory footprint. So memory footprint may be a much bigger issue in the long term than speed, because this is something that is hard to. There's only so much we can buy on a single computer. All right. So now these are the two aspects which we think we can improve on, both memory usage and runtime. Okay. So there's been an argument. Some people say, well, R is really a wrapper language. It's a language that people use just to go to C, right? They say, I've heard that said that, well, there's no point in really speeding up R. You should speed the C functions people call. So we did look at the breakdown of C versus R code in popular packages. So these are bioconductor packages, and the y-axis is lines of code. The red is the amount of C code, and the blue is the amount of R code. And the only point I want to make on this slide is that there's more R code than C code. So people will tend naturally to code up as much as they can in R. And what that means is, you know, you will see some of those worst cases that I showed in the first slide where you're really slow because you're doing all of your computation in R or most of your computation in R. The other thing about this R versus C split is if you're building a compiler for R, then the compiler is very good at optimizing R code, but as soon as you hit a C call, the compiler knows nothing, right? So the more code you put in C, if you have a high-performance R compiler, the slower your system will be because your system will be very good at optimizing your R code and then suddenly hit this black box and say, oh, I don't know what's happening here, so I'll assume the worst. And the worst is that the C code can change anything in the system. So, so the point here is, you know, people write a lot of R code, and you know, pushing things into C is not a solution long-term for performance. What you want actually is turn everything into R code. So as a sort of side note, for many years ago we were working on Java virtual machines, and in Java there was sort of the same thing. People said, oh, if you need performance, just rewrite it in C. We were working on a Java compiler, and every time we took C code and rewrote it in Java, we sped up our benchmarks. Why? Because our compiler was now able to look at the code and analyze it and optimize it. So going to C is not necessarily going to be a good answer for all things. All right. And the last sort of introductory slide I wanted to show is this, which is a comparison of what is the state of other languages. Other languages that are a little bit like R, which are interpreted and high level and maybe don't have so many type declarations. So this is a slide that these are measurements from a colleague at Oracle, and what it compares is it's again these small programs from this computer language game, and they're looking at the performance of C, Java, JavaScript, Perl, PHP, and Python. Numbers are normalized to performance of C. The scale is in, thank you. Scale is also log scale, and what you can see is roughly that the green bars are Java, and the green bars are, yeah, you know, usually about 2x of C, with one case where it goes to 8x. So Java is roughly 2 times slower than C. That's a takeaway for this set of benchmarks. And then the other thing that is interesting is the performance of JavaScript. JavaScript is a very dynamic language. It has some similarities to R in terms of language characteristics. And you can see that where it runs, so we have numbers that are close to Java and maybe between Java and 10 times the performance of C. So JavaScript is less than 10 times slower than C. Okay? And then you have Perl, PHP, and Python, and they're all very slow. They're all in the, well, what can we say? Between 50 and 100 times slower. And the difference between these languages is that Perl, PHP, and Python are interpreted. So just like R, they're running an interpreter that takes every bytecode and figures out, oh, what is this operation? It looks like a plus, let's add things. And JavaScript and Java have just-in-time compilers. So they're running native code that is generated as the program runs. So where would we like to be with R? What would be a reasonable expectation? So currently we're maybe a little bit above Perl, right, in terms of performance. What we would like to be is maybe a bit slower than JavaScript, or around that, around that. There's no reason why we shouldn't be as fast as JavaScript. And maybe we should be even hope to be faster because R has a lot of regular computations. JavaScript is much less regular than that. So we would hope that we could do better. All right. So, any questions? Does that sound like a good goal? Yeah?
What's the speed of SAS versus R?
That I couldn't tell. Does anybody know how SAS runs?
Slow.
Sorry?
It's a lot slower.
Yeah.
It's all over the map.
Yeah.
It depends on how much SAS is open in the runs. It's all over the map.
Yeah, so the bottom line is it's hard to, to generalize for these benchmarks. So I'm not trying to tell you this is the speed you will see. I think you have to test the programs that you care about. Yeah, and I have no experience with SAS. There was another question?
I was thinking about Julia.
Ah, well, we have the Julia folks in the room. How fast is Julia?
We're like down there on that bottom line.
You're there or
yeah, there. Yeah.
About here, so about Java speed?
1 to 2x C.
1 to 2x from C.
Yeah.
Right. So, could we get there with R? It would be harder. It would be harder because R has, by design, made many things dynamic. And I'll tell you about that in a bit, why it's going to be hard to hit that. Yeah.
Can I ask, when you say that, have you guys actually done these?
Yeah, we have these exact benchmarks.
Oh,
yeah.
Like he said,
Everybody does them. They're easy, right?
So we have to,
Yeah. They're not super representative, right? I mean,
Yeah.
but they're a data point. So there are sort of two reasons why R is slow. And there's one set of reasons is sort of micro, you can think of microeconomics. So imagine this piece of code. So I have a function f that takes two arguments and just multiplies them, right? It's easy, simple, nothing too much going on. I have a global variable a that is a random number, all right? Fine. And then I have a function g that assigns 42 to a local variable b, calls f with the sum of a and b. So a really simple piece of code. If this was compiled by a C compiler, what would happen? Well, a would be a global variable, g would be a function, and the compiler would say, well, this is a local variable that holds 42, probably, assign it to a machine register, then a plus 42, yeah, that's a simple expression, so it's an add of a read of the global variable, and maybe the compiler can even get rid of the register and use b as a constant. Then f is a known function. Well, we could actually inline it, and then we see that we are multiplying 42 plus a times 2, so we can simplify all of this into a very simple machine arithmetic expression. So that would run super fast in C, right? Okay. What happens in R? So if I'm just looking at this function here, the R compiler has to create a local variable, b. So for this, it has to get the symbol b, the string b. It has to put it in the environment. So there's a hash lookup that's going on. Maybe we'll allocate a little bit of space for it. It has to create the scalar 42, so that's a 56 byte of allocation. You put 42 in there, you bind it to b. Then you come to the call here, and well, you can't do this addition, even though you have all the numbers here. So you're going to allocate a little bit of space for a promise that says that will remember the source expression, a plus b, just in case you want to do reflection over it, and we'll keep a pointer to the environment, so we can find what b and a's values are. Then, in order to call f, it will have to do a lookup. So it will look up in the local environment. It won't find f. It will look up in the global environment. It finds f. It gets f, checks that it's a function, and then it will have to perform argument matching. So it will allocate a linked list for the arguments. It will try to figure out which argument this corresponds to. In this case, it will correspond to the first one. Then it will find that y is missing, so it will plop in the default value of y. So it has, in order for that call to happen, it had to allocate a list. It had to walk it actually walks 3 times over the list of arguments to get them in the right order and fill in all the missings. And then it performs the call without having evaluated a plus b. Within the function, it's going to say, well, x, oh, that's a promise. It hasn't been evaluated, so I have to evaluate it. So it will go and look up in the environment what is A, it will look up in the environment what is B, then it will look up the value of Y, it will do all the math. The math is all generic because maybe these are vectors, maybe these are anything, so it's all going to take, so this piece of code will take thousands of instructions in the worst case. Whereas in C, you would get it in two native operations, plus and times. Okay. So that's sort of the micro reasons why R is slow. And if we're trying to compile this piece of code, we can't compile it the same way a C compiler would do. Why can't we compile it the same way? So look at this function G. So if I look at this code, well, this looks all very sane and simple. And I could just say, well, why don't I just optimize G to do what is obviously an addition and a multiplication? The reason why I can do that is the next instruction after I've defined G, maybe I'm going to redefine F. Say I redefine F to be this. So now here's a new F function, and for fun, I've decided to just give it a single argument. That I'm completely allowed to do that. And the first thing it does is it redefines the global variable A to now be a vector. Okay? And then it returns X. So what will happen is when we evaluate X, A plus B now is not addition of 2 scalar numbers. It's addition of a vector and a scalar. Completely different operation. I can't do anything. As a compiler, I'm stuck. There is no way I can compile the G function efficiently. I have to leave it completely open, because anything can change. Turns out that in R, I can even change the open paren and redefine it. And people do. There's at least one package that does. So that means, very locally, your code is hard to optimize. It's really difficult to generate efficient code for R. And then there are sort of more macro reasons, which are not local to one piece of code, but are more global around your program. And I'll try to explain this with this piece of code. So imagine I have a function, and what that function does is it allocates an array of 1,000 numbers going from 1 to 1,000. Then it allocates an array, a vector of 1,000 zeros. Then randomly it sets C to either A or B, and then it overrides the first element of C with the number 42 and returns C. All right. So if this was, if I had a compiler, I could probably do this with a single allocation. I would need, if I had a compiler that could analyze, this code, I could probably allocate an array of 1,000 entries and either fill it with zeros with a 42 that leads it, or fill it with, the 42 and then 2 to 1,000, either or. But it's easy enough. What happens in R? in R, I'm going to allocate an array of 1,000 at A. I'm going to allocate an array of 1,000 at B. At C, I am going to duplicate or remember that either A or B is shared, because now I have two references to one of those arrays. And then when I hit this statement, I'm going to duplicate the vector, either the A or B vector. So now I have 3 vectors of 1,000 that I had to allocate, and I'm going to return that. So the problem is the semantics of R are such that your vectors will be duplicated on write. So as soon as you write into a vector that may be shared, a copy will be made. And that is really hard for a compiler to guess, because this can happen. I'm showing this within a function, but really this is depending on how your values flow through your program, depending what you do to them, you will get copies here, there, and you never know where. It's really hard as a programmer to guess if you're going to hit a duplicate or not. And if you're duplicating 1,000,000 elements a bunch of time, it starts to, to be felt. So what is the reason for this? The reason for this is we wanted to have to give the illusion that it's a mathematical language with referential transparency, that expressions, that the changes done within the functions are not seen by the caller, and this is why all of this is set up. So it's trying to be a functional language, but for efficiency, there's this sharing and there's duplication on the right. But what it means is the performance model of R is very hard to understand. So sometimes you create an array, you bang on it, and that's all it happens. And sometimes you create an array, you bang on it, and suddenly you see duplications every time you bang on it, maybe. So it's very easy to write code that will be really slow. And conversely, as a compiler, it's very hard to optimize our code. Okay? Any questions?
So both this and the slide before, would some of these same arguments apply to something like Python?
So Python doesn't have the same semantics for vectors.
Right.
So that's a plus. And then Python, so I'm not an expert in Python, so take this with a grain of salt, but I believe that Python is not as dynamic as R.
I think
so the ability to redefine the plus symbol, or to reach in your environment and start adding and deleting local variables are not there. And that makes things a little bit easier. But up to a point, yes, they apply. I think I haven't seen a language that is as hard to optimize as R. Right? I think it's somebody should give the R designer that particular prize as probably the hardest language to optimize. At least the ones I've encountered and played with. Compared to R, JavaScript is the beauty of elegance and good design in those particular terms. This said, I think R is. I have all respect for R. Sometimes computer scientists like to bang on the mistakes, but it's a very useful language and it does a lot of good. So that's why we're trying to help. But there are many things that don't make life easy. All right. So how to make R run fast? Well, a number of people are trying, and I wanted to have one slide that summarized the state of the art in implementations of R. There's actually quite a few of them going on. Most of them you probably have not used, but here's a list. So the first two are two versions of GNU-R. I'll separate them just for just a little bit because they have different characteristics. So there's the basic GNU-R, which is an abstract syntax tree interpreter. So that's the GNU-R that runs by default. And then also with that comes the bytecode compiler. So R has a bytecode compiler. I don't know if, is that everybody knows? Yes? No. So it's hidden within the R code. You have a flag that said just-in-time compilation. And what that means is, rather than evaluating which are, abstract syntax trees, the R system will generate a sequence of bytecodes, and that sequence of bytecode is more efficient to evaluate. It's about twice as fast. Okay? So the bytecode compiler is twice as fast, but it doesn't run native code, right? It runs bytecode. That's the important thing. It's just it is a translator from abstract syntax tree to a sequence of bytecodes. And that was written by Luke Tierney. It's in all our releases, but it's not on by default. That's an interesting thing. It's not on by default because there's a handful of packages that break when you set it up, when you choose the JIT compiler. Why do they break? Well, because the bytecode compiler does make a few assumptions about sanity, such as that you're not going to redefine plus, that you're not going to redefine open paren. The bytecode compiler, when it starts, looks, if you have redefined any of those operations, if you have, it will not do certain optimizations, but if you haven't, then it'll assume you won't. And some packages do, right? So you start it up, it looks at plus is plus, it says, fine, I will optimize your code assuming plus is plus. And then you sort of define plus to be times, and then everything goes wrong. And actually packages do that, and those packages break. And that's why it's not enabled by default. So there's this compatibility column here, which I sort of listed. It's a completely arbitrary evaluation, but it just means it is not quite always going to give you the same answer as your default R. The answers are, yeah, okay, so that's, and there's other differences with error messages and things like when you print the debug information where you are in the code. All of these things sometimes are used by programs and then they cause tests to fail. So that's why the bytecode interpreter, even though it is twice as fast, isn't enabled by default. And it's actively being developed. So I have one of my collaborators that's working with Luke Tierney, and we're keep pushing changes. Currently, what we're trying to do is get the bytecode compiler to be, fully compatible. Then once it is, we can just make it the default, and that would be that. Then there is a system called PQR, for Pretty Quick R, by Radford Neal in Toronto. And that is a fork of one of these slightly older R interpreters. It adds parallelism, it adds a few optimizations, it is generally faster. I haven't evaluated how compatible it is, so my guess is it's probably close to fully compatible, but I don't know, so one would have to really check. And I've put the websites up there. So the next system, CXXR, is a variant of the R interpreter that's being developed at Google. It started out the project at the University of Kent, where Andrew Reynolds wanted to rewrite the internals of the interpreter in C++. So if you ever look at how R is written, it is very 1960s style C code, right? Full of macros and not entirely, all right, 1970s or 80s, but it's still not, it's not very, very pretty. People are cleaning it up. Eventually it'll become, maybe a modern C code. But so CXXR wanted to clean that up. They wanted to have object-oriented abstractions. So that was what they did at Kent, and now Google has taken it and they want to push it into a new RVM. And so we were talking to collaborate about the collaboration. They're also planning to use LLVM as an optimizer. And I list it as highly compatible because there are some differences, and it's likely that there will be some packages that fail with that too. Then we get Orbit. Orbit was a project at UIUC from Dave Padua, and it was a fork of the R interpreter with some optimizations. And it was an experimental project. The code is out there, but it's not maintained anymore. It was getting about between 2 and 5x speedups. TERR, T-E-R-R, is the TIPCO R implementation. So TIPCO is the company that after a number of acquisition, I guess, owned the S language. And now they're doing a version of R that is should be, well, a clean room implementation. They have looked at none of the GNU code, so it's all done from scratch and proprietary. So that's the only system in this slide that isn't open source. I don't have much information. I expect eventually they'll get full compatibility. And they're certainly working hard on it, but I don't know much more about it. I've never tried it. Then there was a system called Repose at Stanford. It was a just-in-time compiler that targeted GPUs and got really good speed-ups on GPUs. As far as I know, it's not being developed anymore, and it wasn't fully compatible or even highly compatible. It was really targeting a subset of the language as a PhD thesis to try to show how much you can go with a just-in-time compiler and GPUs. Oh, I should have switched those. Then there's two versions of this system called FastR. So FastR is a project we worked on at Purdue, and we started about 4 years ago on that one, and then which was transitioned to Oracle, and Oracle is pushing on with that project. So both of the versions of FastR, both the Purdue and the Oracle one, were written in Java, running on JVMs, and and I'll tell you a little bit more about them in a bit. Then there is another interpreter called Rangin that is from a company in the Netherlands, and that is again a Java version of R running, Java implementation of R. So the benefits, for instance, that Rangin has is you can run Java, you can run your R code in a browser, because you can run an applet, load it up in your browser, and poof, it runs. You need to install nothing, it's portable. Very portable. And the last one is the system we're working on currently, which is a C++ LLVM implementation, where we're basically replacing the interpreter. We're keeping the whole of GNU-R intact. We're just replacing the interpreter with a just-in-time compiler that calls onto LLVM. Okay?
No Microsoft?
Microsoft. Why? What do you mean? No, Microsoft offerings.
Yes.
So Microsoft purchased Revolutions, right? So one would imagine that eventually they would come with something, but they haven't yet, or at least they haven't shared it with us. Right. So, out of all of these, each of these systems is targeting slightly different things. Some of them are experimental prototypes, others have the intention of eventually being used widely. Certainly, our goal is to be an alternative to the mainstream R eventually. So what is eventually a couple of years, right? So R is a very complex system, and getting reasonably high compatibility is really hard. And I would say that I started the project, the FastR project at Purdue, and we sort of underestimated the problem. We thought R is just a language. How hard can it be? And we know how to implement languages, so in 2 years we'll be done. We'll move on to something else. And so 2 years later, we could still not run the Hello World program because we couldn't load any package. We were, limited to the number of things we could run, which was about the 12 programs I showed on the previous slide, plus a few. So it was an incredibly frustrating experience. And so the lesson we got out of that was, we can't redo the whole of R. That's never going to work. We have to sort of target and reuse as much of the existing ecosystem and just replace one piece at a time. And that's the hope we have to actually having impact eventually. Oracle is pushing on with that idea of redoing the whole of R, but they have resources, right? They don't have 3 grad students. They have actually lots of implementers and so on. So they may be able, they'll probably pull it off. But yeah, that was not something we could afford. And the other thing is, my feeling talking to the R community was that an implementation written in Java would not be acceptable. Essentially, the core R folks I talked to say, no, right? They understand C. They could perhaps imagine C++, but it's a stretch. But Java was a non-starter. So okay, fine. So that was a couple of years spent to learn that lesson. But we did learn some lessons. We did learn some lessons from the Java effort, and I think some of it is kind of interesting. So what we did in the Java land is we started with this idea of an abstract syntax tree interpreter. We said, all right, we will take that idea and see how far we can go with this. So without just-in-time compiler, just building an abstract interpreter. And what we got in the end was, so here's a performance chart, and it's breaking down again those 12 programs. Here there's more because we had multiple versions of those programs. And what it's showing is the performance normalized to the abstract syntax tree interpreter of GNU-R of the bytecode compiler in blue, which is, as I said, roughly twice as fast, and the Java implementation of the abstract syntax tree compiler, which is about 8 times faster. So we managed to get an 8 times speed up, even though we were running in Java, which is twice as slow, and not doing bytecode compilation, which wins you about 2x. So we managed to get quite a lot of speedups. And as a comparison, on the same program, Rengine, which is also written in Java, is roughly about 2 times slower. So it was quite an achievement. And and I think the takeaway is a lot of the benefits were because we could do very high-level optimizations. And roughly the idea of the kinds of optimization we were doing is going to be what I've spent the next few minutes on. So we started taking the parse trees that Antler produces for our programs, and we did a very simple transformation to our executable trees. So our trees, so we took our programs and we created these syntax trees that represented the R expressions, and they were written in Java, so they were Java objects. And the way the program was running is, as we run, we were looking at the abstract syntax tree, and we had some state of the program, and then we would rewrite the abstract syntax tree to an optimized abstract syntax tree. And as we were doing that, we could discover very high-level optimization, ways to perform the same operations faster, better. And if the rewrite failed, if the next time, so this was an aggressive speculative optimization. We were saying, oh, I see this state of the world, but I think this state of this program, this AST would run faster. And if we're wrong, we could always rewrite ourselves back to the original AST. And we had this idea that you can take an AST, you can keep rewriting it as you go along, always trying to make it better. And to give you an idea, here's what this would look like. So if I have a function call, this is a function call f to function f that takes 3 arguments. One of the arguments is a named argument, and and the function f takes also 3 arguments, its definition, except the named argument a is the first one. So when R has to run this call, it has to allocate a linked list, it has to search using string search where the named argument should be, and it has to reorder the list, and then it can call the function. So that's a lot of work, and you do that work every time you call the function. Every time you're going to allocate a list, search for where A is, find its position, swap. And if you call this instruction repeatedly, you do exactly the same work each time. Silly, right? Why not remember that work? So the code specialization step, so when we were running, we would represent this program as an abstract syntax tree of the class genCall with 3 expressions. So what we would do then at runtime is we would see, we're calling this function f, and argument A is the 3rd argument, but it should really be the 1st. So why not rewrite this to a special call? So rather than a general call, this is a positional call, and we've put the last argument from, so we swapped the order, and then we remember which function we want to call. So now, next time we come to the same point, we're going to check, is f still the same f? If it is the same f, then I don't need to allocate that list, reorder, sort, nothing. I just jump to the code, I have the arguments in the right order. Right? Very simple, high-level optimization that you can do, and what we're leveraging is the fact that the same instruction, the same point in the call typically calls the same function. So we're speculating that next time around we're going to call the same function, and therefore we don't need to do all that work. Now, if this is wrong, if somebody redefined f, then we have to undo. We have to get back to the old code, get all the abstract syntax tree, and start from scratch. But it doesn't happen much, so this speeds up the program. So how does this look in Java code? In Java code, for instance, we would have code, so this is the implementation of the if node. So in the abstract syntax tree, the if node has 3 subnodes, which are conditional, and the true branch and the false branch. It has an execute method, and this execute method speculatively says, I believe that the code of the conditional returns a scalar logical. That's what you expect, right? You expect that the if evaluates, the condition evaluates to a single logical value, true or false. So what we're putting in the code here is this speculation that we're going to get a scalar logical, and then depending if it's true or false, we're going to execute one or the other branches. Now, this may not be true. That's just a speculation. Maybe the if has an array of scalar logical, in which case we need to extract the first one of them. What happens there is the code throws an exception in Java, and the catch will rewrite the node to a more general node, a node that knows how to deal with arrays of scalar logicals or so on. So there's nothing too deep about this. All I'm saying is, by leveraging information that we have at runtime, by leveraging what we've seen and the state of the system, we can optimize our code. And we do similar code specialization for arithmetics, for vector indexing, all sorts of things like that. Then another interesting optimization is data specialization. So what we did is we observed that a lot of the code was looking for things that had, for instance, that were integers of size 1 that had no names, no dimension, and no attributes, right? So this is code that is really looking for just a number. You know, if this is just a number, I can do something. So what we did in the system is we could replace the implementation of the data type with a special data type that had exactly those characteristics. And rewrite the code from having to check all of these things to just having to check, is this a scalar int? If it is, then do something else. Another thing that we noticed is R has a lot of loops like this, where you're going I over 1 in n. And in general, what R has to do is you have to allocate this 1 in n as a vector. So you're allocating, if n is 1,000,000, you allocate 1,000,000 elements. And that seems incredibly wasteful just to iterate through it, right? So what we can do is we can replace the implementation of the vector with, you know, just an object that remembers, oh, I'm an iterator between 0 and n, and my current position is this. And that's 3 numbers instead of 1,000,000. So that's a win. And this is how we implement it in Java. We create a new class called rint simple range that is a subclass of rint, and it has 2 numbers. No, it has a 2. I think it's just right. Yes, it's from 1 to a bound, and we can iterate through it. And if we need to turn it into an actual vector, we have code to materialize it. But most of the time we don't materialize it, and we save space. And the last of these optimizations we did was the following. When you're in R and you see code like this, you see A is assigned B plus C, and then O is assigned A times 2. What we do is, rather than evaluating B plus C and A times 2, we delay the execution. We turn it into a graph, and we evaluate the graph on demand. So, you know, we turn it into this graph, which is sort of has all pointing to a star node, a multiplication node. The multiplication nodes points to a plus node, and to the 2 constant. And then what we can do with this is, if you don't need all of the values, well, we never compute them, right? If we don't need to compute temporaries. So in R, A would be a temporary object that I would create. I don't need to create that, and so on. So by delaying, you get, again, a lot of benefits. And lastly, we had optimizations such as we would create, even for a simple expression like B plus 2, we would create a view that would just count how many times you use it, and depending on how often you use the result, would generate a different representation for it. So, all this to say is, we started with a Java implementation of R, which doesn't even do bytecode compilations, which should be way slower, and we got 8 times faster by a lot of these tricks. Now, can we use those tricks in the real R? No, we can't. Why? Well, because the real R implementation has exposed the internals of R to all the libraries. And it's really hard to tell whether a library is going to start picking and poking at values. What we would like for optimization is to have APIs. You know, have the library talk to an R vector through an API, and then behind that API we can choose how we're going to represent the R vector. It's really hard to do. That was the whole challenge for us. You know, we could speed up R a lot if we can change the representation of things. You know, by the nature of the APIs, which is essentially a bunch of C macros, anybody can touch anything, and it's really hard to tell. So since then, what we've started doing is we're writing code that analyze the C code of your packages. And we're trying to figure out what the packages actually do. And if we can find that there are some things that the packages don't do, then maybe we can take advantage of these. But that means we know we have to analyze the code of thousands of packages, and there's always one package that breaks, that does something crazy. And then you're asking yourself, well, is it okay to break that package? The hard choice, right? If it's a package that you care about, certainly no. If it's a package nobody uses, probably. All right. So what I was telling you about here are sort of high-level optimizations. These are optimizations where we sort of change the structure of the program, change the structure of the data. And there's another set of optimizations which we can do, which are more low-level at the statement level, micro optimization we call them. And these can be done easily by taking R and trying to compile it using LLVM. That's one of the things we're working on. So currently, the GNU-R system looks like this. Take source code, parse it to an AST, and either you interpret it or you compile it to bytecode and you interpret that. That's the current pipeline. And like I said earlier, both of these interpreters, these two interpreters aren't exactly giving you the same result all the time. So what we started working on is a system that takes your AST, and from the AST we generate LLVM intermediate representation, and on that representation we do some optimizations, and at some point we can drop to native code. Okay? So I can show you how this looks, just to break the slide flow. So if I start up the R environment, I can, let's see, what can I do? I can load the compiler. So this will load the compiler. So let me define a few functions. So I've prepared some mostly uninteresting bits of R code that do stuff. So I define F, G, and H as 3 functions. And now I can compile them. So how do I compile a function? So for instance, I can say, I can say F compiled is jit.compile of F. So what this will do is it will take the abstract syntax tree of the R code and generate a piece of LLVM intermediate representation, optimize it, then generate native code. So and from there you can still call back into normal code. So I can call F. And F. This is, if I call F, I'm calling the interpreted F, and it takes a while to run. No, I don't know. I'm not a patient person. Yeah. All right. So and it gives us a wonderful number, 0. If I call the compiled version of F, it actually won't run much faster because I've compiled the F, but F spent most of its time calling uncompiled code. So it's not going to make much of a difference. So let's compile everything. That'll probably. So maybe we should time this. Let's time the old F. How long does it take? If I print of system time, it should be about 10 seconds or so of execution time. So it feels longer. 15. So now I can call this. Let me define a helper function. Recompile. So what? No, that wasn't I wanted to do, come on. Sorry. I wanted to paste a recompile function that will recompile all three pieces of code. All right, so it's, yes. So recompile calls the compiler for all three functions. So if I recompile, I did, yes. Too many O's. So I've recompiled them. Now I can, so now they should call the LLVM native code. So if I print system time, it should be tad faster. Actually, not so much, because it turns out that if we don't do any real optimizations, the wins are fairly small. So we went from 15 seconds to 11 seconds. And this is really just the cost of removing the loop or the interpreter loop. And you don't get that much. If we have started to implement some actual optimizations. So, for instance, we have infrastructure to record types when you call a function. So, so for instance, so if I set this flag and I recompile my code, I will generate. Oops, that was not what I wanted to do. I will generate another version of my code that records all the types of the arguments to functions, and then that will actually be slower, but it will allow us to, yeah, it's a bit slow. But now what we can do is, if I ask the JIT, for instance, print the typed feedback for H, it's telling me that the argument to H is a float, so it's a number, and it's a scalar. And the second argument is again a float. So now it's looked at the computation. It's told me, oh, all of this function is always called with floats. So we have another flag that we then put, which is, for instance, recompile hot. And what this says is, if a function generate code that will count how many times a function is called. If that function is called many times, try to recompile it and optimize it using the type feedback that you got above. So now we can recompile and run the system. So now we take these three functions, we generate a new piece of LLVM IR, a new native code, and it runs in 11 seconds. So that's still not that much better. And I think there was once, oh yes, and currently we haven't finished optimizing, we're still in the process of writing the code that will use the type feedback. So there's a flag that is called unsafe, which says, do the optimizations, even if you're not sure that this is going to be right. It so happens that for this simple program, they're fine. In the real world, we would have to do a little bit more work, and we're working on it. But if we recompile now with this unsafe flag, it ought to run a little bit faster. Is it 10 seconds? Yeah. So we went from 15 to 10 seconds. And there's another bit of optimization we've done is, you remember I was telling you that R has to do this shuffling of the arguments. So what we do in our system is we do the shuffling only once, and then we remember it. So we compile a little piece of code that remembers the shuffle, and we always call that same shuffle again. So if I set this flag, it may run yet. So this is the static name match flag, and it should run a little bit faster after that. So And let's see what happens. 6 seconds. So, yeah. So we went from, what was it, 15 to 6. It's okay. I mean, it's not super exciting, considering that this is really simple code, and you know it's 400 times slower than C. So we should really, we should really run this in less than a second. But hey, this is where that particular system is. So I can show you a little bit what the LLVM IR code looks like, and the answer is it's not pretty. So there's a flag.
What does IR stand for?
Intermediate representation. So LLVM has a format for its instruction, textual format, and this is what I will print. So if I ask for print IR, and I say, well, I'll just type a new function. So I say JIT.compile of function that takes X. I don't know, add two numbers, X plus 1. That sounds simple enough. Yeah, it should be simple enough. So, poof. All right, so what is the code looking like? It is barely readable. So what is going on? Well, so there's all of this stuff I was telling you. I was telling you about this type feedback code, about this recompilation. That adds code that is added to the LLVM-IR. So the LLVM-IR does have to deal with, every function now has a counter, every function keeps track of the types that come in. There's code for the garbage collector to run. There's, it becomes very messy, but it still runs faster, right? It was running in 6 seconds instead of 15. So even though we've bloated the code, that's just what the compiler has to take care of. All right, so I think that's roughly all I had. So I just want to say one more thing. So we've got a bunch of optimizations. There are some optimizations that we tried in the Java system. And they were hard to port to GNU-R because they need changing the data structures. There's these optimizations we're doing, which are, we can get to some, I think we can get maybe a 5 or 10 speed up over R, which is not bad, but there's a limit. If we want to go beyond that, we have to sort of investigate, slightly more disruptive changes. What the Julia team is doing, for instance, is to add type annotations. So, are we feeling, in the mood of adding type annotations, even optional? If we could add type annotations, we could go faster. Or are we feeling like we can restrict some of the more obscure features of R? If we could do that, we could speed up R. There's a number of things, and the question is, well, there's a point where we have to choose, like we say, well, maybe there's some packages we will have to break. The question is, how many packages can we break before people say, yeah, this is not my R, I don't want you to do this? And that's a question that's not easy for me to answer. I know how far we can get just playing compiler tricks, but it's limited because R is really, really dynamic. And yeah. So that's the summary. So we're working on this. We're happy to get either, if somebody has slow R code, we always like that as good examples, or if anybody's interested, we're happy to collaborate on any related topics. Yep.
If we were to switch to type annotations, at that point, how different would R be from Julia? I mean, what's the fundamental difference after that?
Well, R is still, if we had type annotation, R would still be very dynamic. I could still redefine anything. I could still walk the stack. So there's still other things, right? Type annotation gets us a little bit of the way, but all of this business of, oh, in R I can add a local variable or delete one. If I delete one, that's funny, right? Because now you have a compiled code that was expecting a local variable to be there that is wrong. So how do I deal with that? So Julia doesn't have that problem, I think.
Correct.
Yes. So it's a language that was designed for, that with the idea that maybe we would compile it. Well, actually, perhaps more than that, but at least that. Whereas R was designed as, oh, this is an interpreter. Here are all the cool things we can do if we play with the interpreter. It's a very different design goals, and some of the cool things that R can do are actually cool, and others are, yeah, we could live without them. The question is, can we separate those and sort of try to deprecate the ones we could live without? Yeah.
Have you ever looked at the packages that you would break and figured out how popular they were?
So we've looked a bit, but we haven't decided in which way we want to break things yet. So that's there's a number of questions there, but we are building tools for analyzing packages, and the goal is to be able to exactly evaluate this. How much breakage is it if we change this feature?
Yeah, because you can certainly end up breaking some packages that nobody ever used.
Yes.
And that's pretty easy now to figure out.
Right. And so we've been pushing also as tests, we've been pushing fixes to random packages, and we're looking at how receptive the developers are to changes. And some are, and others not as much. Yeah.
What is this compiled or compared to Duncan Temple Wang's RLVM compile package?
So the RLVM package was much smaller in scope, so it could do very simple things, and I think it was more a proof of concept. So so we're pushing further, and we're trying to essentially extend it to the whole language. Yes.
The packages that break, are they mainly things that call into the C code and the interpreter directly, or is it actual obscure corners of R as a language itself that breaks? What would you really have to restrict here? Access to the interpreter, or?
I mean, there's a lot of obscure corners, and so you get, So to give you an example, so we're trying to change the way. So the bytecode compiler, the R bytecode compiler, isn't reporting source line information in the same way as the AST interpreter. And that breaks some packages, because the packages actually take the source line information and maybe turn it into code or some such, or God knows. So there is a lot of really, really weird stuff going on. And some of it we can't, I mean, some of it, eventually we could support everything, but the question is how much speed up we would get, and
R has a couple ways to make things faster if we bank off Julia or CPP, the C++. I mean, is it at all an advantage to R to cut its losses as being fast itself and just making it extremely easy to integrate anything and everything that would be fast? Is that
so the question is making it easier to write native code? Yeah.
Being able to call libraries in a second that allow you to write any language and just be able to take advantage of all their strengths instead of trying to be R and I do everything.
So the challenge is the semantic mismatches between the languages. Things like the fact that as soon as you go outside, you have to so R has very peculiar semantics. Like for instance, the assignment on write. If I pass a vector to another language, what can I assume it does? Will it write to it or not? Now, if the vector is shared, I have to duplicate it. So there's a lot of pessimization that happens at an interface. Whereas if it's written in R, I can see that, even if I don't have an optimizer, if the vector is not updated, I don't need to duplicate it. Worst, and the R implementation has to take the worst case. It has to assume that the C code or the Java code you're calling is going to bang on the vector, so there has to be a copy. and copies are killing your memory performance. So, you know, so just the boundary as we have is not good enough, right? It's not, that would not, so what we've seen is, if your code is one line of R code that calls into C, perfect. Why do you need R, right? Just use C. If your code is a lot of crossing the boundary, then things go much slower. Because at those crossing, you lose performance. You're transferring data. And the higher level the language, the worse it is. C is sort of easy because you pass in the raw bits and you give them back. But if you had to go to Java or Python, you now have to create objects in the Java land, and it gets really, really messy. So it's hard to do inter-language communication efficiently for those semantic mismatch reasons. It's my gut feeling. All right.
Let's thank our speaker.